this is a joint work with Benny Yoshida. And let me start with the motivation. The motivation comes from the study of quantum black holes, although the work itself is just quantum information. So there are different ways to understand a quantum black hole. First, one can consider quantum fields on a classical background, and that was done by Hawking 40 years ago. And the main results, I'm trying to find the laser pointer button. Yeah, the main results are these. There is a temperature that is related to the surface gravity kappa, and entropy that is related to the horizon area A. The second level of understanding is information scrambling. There is a so-called scrambling time at which everything that falls into the black hole is scrambled with what was there before, and it's given by the same number kappa, inverse kappa, times logarithm s. So it's just slightly longer than the Schwarzschild time. And gravitational interactions occur between incoming and outgoing radiation. This idea of gravitational interaction between these two particles is due to Harold Hooft. And Drain Hooft first found classical shock waves that are formed in the black hole due to the incoming radiation, actually incoming particles. Any incoming particle will produce a shock wave along this line, the path horizon, that will affect outgoing particles. And Hooft also studied a quantum version of this effect. However, for a long time, it wasn't obvious how to characterize this effect in terms of observables, and this is the way to do it. One has to consider out-of-time order correlators like this, operators x and y applied at time 0 and z and t at time t. A thing like this is never measured in a usual experiment except for some very complicated and sensitive settings like Loschmidt-Echo. One needs to evolve the system forward and backward in time. And this correlator is sensitive to the interaction between the incoming and outgoing waves, unlike usual correlators. And the third level of understanding is evolution over Page's time, when half of the black hole evaporates. This needs full quantum gravity, and it's not clear how to do this. I'll talk about that part in a quantum information setting. It's highly idealized. So in quantum information, we first replace the black hole, which is a thermal system at temperature T, by a typical subspace. So this is the density matrix of a thermal system, and we identify a typical subspace whose dimension is exponential in the entropy. It's e to the s. I'll use binary units, so it's 2 to the s. And we consider the maximally mixed state on the typical subspace, which is not a perfect approximation to rho, because rho and the actual rho and this approximation are far apart in terms of the trace distance norm. But they have similar characteristics like entropy and other things. So I'll use this abstract model. The density matrix is just proportional to the unity matrix divided by d, where d is 2 to the entropy. And the second assumption is about late time out-of-time order correlators. We consider late times times greater than the scrambling time, and it is expected that at late times the out-of-time order correlator factors like this. So if we take x, y, z, w to be operators with zero mean, then the right-hand side just vanishes. Otherwise it's this quantity. W is the evolved operator W. It's the W of t is the evolved operator W. And instead of the Hamiltonian evolution, I'll use just some unitary operator U. Now, this identity holds if U is taken to be a higher random unitary. And we average both the left-hand side and the right-hand side over the randomness in U. But it doesn't have to be random. It can be a fairly general but complex unitary operator like the Hamiltonian evolution of a non-integrable system over some extended time period. And if it's not hard random, we have to assume that these operators W, Z, Y, X act on small subsystems. For higher random unitaries, this identity holds for all operators X, Y, Z, W. For more general use, it's required that these operators act on small subsystems.
Excuse me? Yeah. What is the relation between the evolution Hamiltonian and a black hole, something like this?
Oh, yeah. Thank you for asking this question. I skipped the introduction part. I have to do it. So a black hole is just a quantum system. We don't know its exact Hamiltonian, but there must be a Hamiltonian. So this system evolves in time, and we can calculate the evolution operator over a particular time. This is one point of view. It's a black hole is a black box. We don't know exactly what it is, but it's characterized by some rather complex unitary operator. Of course, it would be nice to connect it to what we know about black holes from general relativity. I won't do that, and it's of course very interesting, but I'll just assume it's some sufficiently complex unitary operator.
You're assuming information is not lost here.
Yeah.
You're not saying that's not reasonable.
Yeah. Right, yeah, this is an important assumption. We assume that it's just a quantum system. Instead of a black box, we could use a black body, a black metallic ball that absorbs radiation and emits radiation. It will be all the same. Now, if there is a complex system that scrambles information, it implements a sufficiently complex unitary operator U, one can ask if it's possible to recover the scrambled information from the radiation. And that question was asked by Hayden and Preskill 10 years ago, and they gave an abstract answer that it is possible to recover information in a certain setting. The setting is this. They actually described a thought experiment in very vivid terms. I cannot reproduce it fully. Alice wants to hide her secret, her confidential diary, and she would like to destroy it, but Bob is spying on Alice, and he could recover the information even from ashes and smoke. So she decides that a black hole would be the safest place to hide the information. So she throws her diary into the black hole, and A is the quantum subsystem that represents Alice's diary, and it's joined with a big system B, which is the black hole. Then time goes on, and the black hole emits some radiation D, and C is the remainder of the black hole. So A and B is related to C and D by a unitary. Now, it would be nice to recover information just from the Hawking radiation. But for that, one needs to collect a lot of Hawking radiation, at least half of the black hole. And the wonderful thing that Hayden-Preskill invented, that instead of using only the radiation, one could ask a different question. Suppose Bob owns the black hole in such a way that he has previously established entanglement between the black hole and system B prime, on which he has full control. It's like a quantum computer run by Bob. And B and B prime are in a perfectly entangled state, in a perfect EPR pair. It's not exactly the physical setting described by Hayden-Preskill. The physical setting would be to wait when half of the black hole evaporate, then Bob collects the radiation and transforms it to the EPR pair between B and B prime. However, this problem is hard, transforming the black hole radiation to B prime that is simply entangled with B is a difficult problem due to, it was shown by Harlow and Hayden. So I'll discuss an easier problem. We know that B and B prime are entangled in a particular way. Every qubit in B is entangled with a corresponding qubit in B prime. And then we can ask about, we're not there yet. We can ask about the existence of a decoder that takes the Hawking radiation and B prime and reconstructs the initial Alice's state psi, a copy of her diary. It will be the same information that went to the black hole. It's no longer in the black hole, but it's here. It's slightly easier to work in a different setting. It's a variant using a reference system R. It's like the worst case scenario, worst case in terms of Alice's secret versus average case. In the second scenario, Alice has an entangled state C. It's entanglement between her diary and some reference system, say Alice's memory, R. And the task is to construct R prime that is perfectly entangled with R. So Bob applies the decoder, but he doesn't recover the original secret directly. He recovers an entangled state between R and R prime in the end. And these two subsystems will be in an arbitrary state. It doesn't matter, but it's important that these two form an EPR pair. Now, this diagram has some special notation. This dot represents a factor 1 over the square root of dimension, and such factor appears in the formula for an EPR pair between B and B prime. And this triangle represents a different thing. Let's discuss this initial state, an entangled state between the reference system R and Alice's diary A in physical terms. So there are a few bits of information in Alice's diary. Each bit is entangled with some bit of the reference system. But the diary itself is a physical object. It has some energy. And one can define two quantities. dr is the dimension of the Hilbert space corresponding to the information. The logarithm of dr is the amount of information. And the logarithm of dA will be the energy divided by temperature. It's the coarse-grained entropy. So this is the information content, and that is the coarse-grained entropy, which is greater. And mathematically, we use an embedding Xi from R prime, a copy of R basically, to A. So it's an embedding of a small Hilbert space to a large Hilbert space. A can be very large because the diary can be heavy. So we're talking about the rest energy of Alice's diary. So we have this triangle that represents this state Xi. It's an EPR pair between R and R prime, and then we apply the embedding. And on the right, we have just the EPR pair. Yeah.
R is much smaller than A.
Yeah, R is, it doesn't have to be much smaller, it's just smaller. Smaller or equal in general. There are two parameters. It's convenient to use both parameters.
Sorry, another layman's question.
Yeah.
When you have the wave function in Alice, state, quantum state.
Yeah. You mean this wave function? Yeah.
But you're working with density matrix and all this, so you don't have two quantum states.
Well, in many cases, it's not important because the protocol is a linear operation, and if it works for pure states, we can apply it to mixed states. So I'm not sure exactly what you're asking.
Is how can you recover completely Alice's quantum states at the end if some information flows to the remaining black hole on your diagram?
This vertical direction is time. Time goes up. So first, Alice's information is mixed with the black hole. And of course, we do not get exactly the same bits of information here as Hawking radiation. But we get enough information so that it's recoverable. Yeah, there is a subtlety. It's not possible to recover information just from the radiation, but from the radiation and B prime, it is possible to recover it. And the remainder of the black hole will not contain any information. Yeah, sure. Right. So in that setting, I use some notation, and this notation is tensor diagrams, tensor networks. In general, nodes represent tensors, and lines represent index contractions. But this particular notation has this built-in notion of time. Time goes up in the diagram. And we use certain rules to reflect that. Vertical sections of lines correspond to Hilbert spaces. But the same line can go down or up. It's the same line. Here it goes down, and there it goes up. And the Hilbert space of a line going up is the dual of the Hilbert space of the line going down. The duality is like one space is the space of linear functionals on the other. It's the mathematical duality between vector spaces. Then, if psi is a vector in the vector space with matrix elements, vector elements C sub j, quantum amplitudes, and psi star is characterized by complex conjugate amplitudes. We can write this thing that represents the ket vector psi. And we can also write this thing that represents the bra vector psi star. They're defined by the same psi, and one may say it's the same mathematical object, this and that. But we keep them separate because they're different in the direction of time. In one case, time goes up. In the other case, time goes down. That's why it's reasonable to keep them separate. And these two things are also kept separate, although they are both encoded by the same psi star. And if in these diagrams we rearrange things and turn some box upside down, if this box is an operator, it has one line on top, another line on the bottom. Instead of turning it upside down, and turning X upside down, we just put this transpose symbol. So this thing and that thing represents the same object. It's an entangled state of A and A prime. It's a vector like this that is encoded by the matrix elements of the operator X. And then I'll show you how this language works. Just bear with me. First, let's discuss the possibility of decoding. And that question was answered by Preskill and Hayden. So suppose the state of the world is obtained this way. The unitary operator U is applied to two copies, two entangled states, the tensor product of two entangled states. One is the reference system entangled with Alice's diary, and the other, the black hole, is entangled with Bob's quantum computer. And then U acts on A and B, and R and B prime are left the way they are. Then we have the state of the world psi and the associated density matrix. And we would like to recover quantum information, or rather recover a perfectly entangled state between R and something else using D and B prime. And that is only possible if the black hole C has forgotten Alice's secret, which means that the density matrix of rho and C factors. It's the density matrix of R and the density matrix of C. And in terms of pure state, it means that if the density matrix factors, it means that R is entangled with something in D and B prime, and C is entangled with a different part of D and B prime. And we just need to separate these two parts. So quantitatively, instead of saying that the density matrix approximately factors, we introduce this quantity delta, and Hayden-Preskill also did that. It's this quantity, which is 0 when this equality is exact. In general, it's greater or equal to 0. If number delta is much smaller than 1, then the recovery is possible with fidelity close to 1. It's almost possible. In our algorithm, delta will determine the decoding fidelity of the whole procedure. Now, let's calculate delta, or rather, let's calculate this quantity, trace rho RC squared. This is the reduced density matrix of the state of the world, where we trace over D and B prime. So this thing on the top is psi ket vector. This thing at the bottom is bra psi. This loop corresponds to taking the trace. And we need to square this matrix and take another trace, because this loop is taking, this loop corresponds to this trace. And when we square the matrix, we take the full trace, so that there are no free ends. And we get this diagram. It's a rather complex diagram. Let's do the calculation. So we have this complex diagram. So we rotate the top part and the bottom part like this. And when they're completely flipped over, we replace U with U transposed and U dagger with U star. And this is the final diagram we get using our diagrammatic language. So the parameter, the fidelity parameter little delta is expressed in terms of capital delta. And this capital delta is just the diagram that appeared before with these normalization factors. These dots are 1 over the square root of the dimension. And one can also say that the capital delta is out of time order correlator between two operators, L and M. And this generalizes a result of this work by Hasur, Chi, Roberts, and Yoshida. We define L to be this operator acting on system A prime A, and decompose it into operators acting on A prime separately. Yj acts on A prime, Yj transposed acts on A prime, and X acts on A. And similarly for M, and the out of time order correlator is defined like this. It's some complicated formula, but this thing in here has appeared before, and it will appear now. So this is the out of time order correlator between X, Y, Z, and W. And diagrammatically, it's expressed like this. And then we say that X and Y transposed, it's kind of one thing, one object. And W and Z transposed is another object. And instead of individual X and Y, we can take a sum over several X's and several Y's and call it L. And similarly, we can use M. And if we plug in those objects, we get exactly that delta. Now, let's use our assumption. At late times, we assume that the out of time order correlator factors. And when we do the calculation on the right-hand side, using diagrams, then Y average times X average is represented by this diagram, and the average value of Y times X by that diagram, and we just calculate the right-hand side and get this result. So this is capital delta. The little delta is defined like that, and we may ignore this term, or we may just say it's negative. This way we get an inequality. So the little delta is, the little delta is given essentially by this quantity. dA and dR are respectively the information, the energy and the information content. And the little delta is going to be small if D, the size of the Hawking radiation captured by Bob, is greater than the square root of dA times dR. How hard is the decoding problem? Although it's possible to decode information theoretically, we expect the decoding problem to scale exponentially with the message size. The message size in this case is the logarithm of d sub a, the number of bits in Alice's secret. And in fact, it scales exponentially with the coarse-grained entropy of Alice's diary. How do we understand that the scaling is exponential? Let's consider a classical variant of this problem. And let's assume that dA equals dr. So everything is information. We don't consider energy separately from information. Classically, we talk about Alice's message, which is just a bit string. A is a bit string. This box is some function u, which is a permutation of bit strings. So it takes 2 bit strings A and B, concatenates them, applies some invertible function u, and we get 1 bit string that is discarded C, and the other that is captured R. Now, if we assume that Bob has an EPR pair, in the classical language, it's simple. It just means that this B is known to Bob. And it's just a constant for the purpose of Bob's calculation. So we may assume that B is constant. The only variable is A. And R is some function of A. So we fixed one variable and discarded another variable. And when we just write R is f of A, f is essentially a random function. It's some complex function, but we may think of it as a random. So it's like guessing a password by trying all possible combinations. This function transforms the password to some string R, and in computer science it's called a hash function. And we want to find A that would give this value R. In general, we need to try all possible A's, although information theoretically it's possible to reconstruct A because the number of possibilities for A is smaller than the number of possibilities for R. That is exactly what this inequality says, that the Hawking radiation, the number of possibilities in the numerator is smaller than in the denominator. But computationally, it's hard. We need to try all the values. So the complexity is exponential in the size of A, but it's linear in the dimension of A. Dimension is exponential in the size or in the entropy. But the main result of this work is that the complexity is linear in C. C is the size of the quantum circuit that implements U. So the complexity scales exponentially with the message size, but not with the black hole size. This is our result. It could scale exponentially with the black hole size. This is a simple version of the decoding protocol, decoding algorithm. It's probabilistic. So what it does is this. Bob captures some radiation and tries to guess the content of Alice's diary. And this guess may succeed or fail. Most of the time it will fail. But if it succeeds, Bob will know that the guess is correct. So it's this kind of thing. The probability of success is pretty low. But we care that we can tell whether our guess is correct or not. So classically, we have R, that is a function of A, and Bob picks a random number A prime. He is guessing A, computes R prime that is equal to f of A prime, and then compares it with R. And this way, he can tell whether the guess is correct or not. And quantum mechanically, you can see different elements common between this and that. This is the initial state. Comparing two things is done by means of the projector, P sub D. It projects onto an APR pair on D and D prime, leaving those subsistence unchanged. And the success probability is given by this quantity. It's exactly capital delta, and it's greater than this number. So the success probability is generally low, but we have a lower bound. So how do we estimate the fidelity of the decoding? The fidelity is the following thing. We have the projected state. It's basically the state of the world projected onto perfect entanglement between D and D prime. This is the operation that most of the time fails. But when it succeeds, it produces the state psi out. And we want to know how close psi out is to the desired state. That is called fidelity. So to quantify the fidelity, we take this reconstructed state psi out, the projected state psi out, and project it another time using P sub r. P sub r is the projector onto the desired state. And the previous projector was something that Bob can do. And P sub r is something that Bob could do with Alice's help, but Alice, of course, won't help him. So we just do it on paper. So if we do the calculation, we use an inequality between this thing, EPR sub D is, corresponds to this projector. And using the inequality, we do some calculation and get an estimate on the fidelity. It's greater than 1 or 1 plus little delta. If little delta is small, then the fidelity is close to 1. The fidelity is a quantity between 0 and 1 in general. But it's more interesting to do the reconstruction deterministically so that we succeed most of the time rather than failing most of the time. This is done using Grover search. This is a diagram. Times goes up. The bottom part is the preparation of the initial state, and it includes the black hole evolution U. But the top part is done entirely by Bob. Bob applies operators WD and this operator WA tilde, which actually consists of several things. And he does this multiple times, this many times. Now, in more detail, this WA tilde is the projection onto, it's constructed using the projection onto psi in, and psi in is the state that is prepared by the bottom part of this diagram. Psi in is just a vector. Psi in times psi in is a projector, but W sub A tilde is a unitary. And WD is another unitary that uses psi out. Psi out is something that appeared on the previous slide, this psi out. And this multiple repetition of WD and WA tilde is similar to Grover's algorithm. And it basically turns psi in to psi out in the following way. The computation happens in a two-dimensional subspace. This subspace is spanned by psi in and psi out, but let's use these basis vectors. The horizontal axis is the orthogonal complement of psi out, and the vertical axis is psi out itself. And initially psi in is a vector that is close to psi out perp. This angle theta is small. First, we apply W sub d, which is a reflection above the horizontal axis. And then, then we apply WA tilde, which is a reflection about this axis, psi in. And the composition of two reflections is a rotation. It's a rotation by angle theta. So if we first apply one reflection and then the other reflection, effectively we have rotated the vector by angle theta. And if we do this rotation the right number of times, we'll rotate psi in to the desired vector psi out. That's the idea of Grover's algorithm. We just need to figure how to implement those operators, which is shown here. So first, we have to produce psi in, and U is the black hole evolution, which is already done. We apply U star. Second, we need to define WD and WA using some projectors, PD and PA. And these are the definitions of those projectors. So PD is projects onto the EPR state of D and D prime. PA is projects on the EPR state of A prime and R prime, and PA tilde, which is actually used, is the same as this one, conjugate by U star. And we apply those unitaries repeatedly this many times with some parameter. So if we analyze the algorithm, let me do it quickly. First, we should acknowledge that the previous description was oversimplified. Grover's rotation do not occur in a two-dimensional subspace. They occur in multiple two-dimensional subspaces. And in each subspace, the rotation is by a different angle. This space splits into two-dimensional subspaces L sub G, and in each subspace, there is a projector PD defined using one vector and PA tilde using another vector. And their inner product depends on the choice of J. The initial vector can be decomposed into those vectors psi G with some amplitudes, and we should also take into account as a technical detail that we also have other subsystems, R and C, and psi sub G should be tensored with some vector on those extra subsystems. And this way we define vectors on larger subsystems. But the conclusion is very simple. If we start with psi in, decompose it this way, and apply Grover's rotation, then the resulting vector is a sum over J, and for each J, we basically have a rotation by this angle in the corresponding two-dimensional subspace. So we define some parameters, and xj is the normalized rotation angle given by this quantity. Ideally, we want x sub j to be 1. And the actual rotation angle is multiplied by pi over 2. Of course, it's not 1, but we show the following. If we first calculate this numbers p sub j on the previous slide, calculate alpha sub j, or rather obtain some identities for them. And if this parameter delta defined by OTOC is 0, then all the alphas are equal and x sub j equals 1 for all j. This is the ideal case. But in general, we may use some inequalities, and we get approximate equalities, that the final vector produced by our algorithm is close to this vector, which is in turn close to the desired vector. And this is done with accuracy square root of delta. So in conclusion, our algorithm is deterministic. It involves this many applications of operators U star and U transposed. U is the black hole evolution operator, so we just need to apply a copy of the black hole evolution multiple times. We simulate the black hole on our quantum computer and do it this number of times. And the fidelity of the reconstructed state is O of delta, where delta is defined by OTOCs. At late time, delta is close to 0. So this is the late time estimate. We also need that the size of the Hawking radiation, d sub d, is greater than the square root of these two numbers. And this is the condition under which the algorithm works. So there are some open questions. We would like to generalize this algorithm to thermal density matrices. We have done it under these assumptions when the initial and the final state factor, but these are unphysical assumptions, because if we think about the actual black hole, it may be in a thermal state, but it must radiate. Therefore, radiation outside the black hole, field degrees of freedom outside the black hole, must interact with the black hole itself. And so the factoring will never be perfect. We don't know how to deal with this problem. We have some ideas, but it's a non-trivial problem. Another question is, in the traversable wormhole story by Gao, Jeffers, and Wall, maybe Aaron will tell us something about this, and also by Alessandro, Stanford, and Young. The decoding happens in one go. But that is assuming the early time regime rather than late times. It would be nice to formulate the necessary or sufficient conditions mathematically in terms of out of time order correlators, and to modify the protocol accordingly. And finally, Grover's iterations bear some similarity with multiple shock waves by Schenker and Stanford. We don't know what the exact relation is, if there is any relation. It might be a superficial similarity. But it would be nice to have some gravity interpretation of our protocol. Yeah, that's it. Thank you for your attention.
Any questions? Hi. Eventually, you want a model of a black hole which looks like a model of a hydrogen atom or something like that. The hydrogen atom absorbs photons, emits photons. You also get entanglement all over the place.
Yeah.
Do you see any fundamental difference between the black hole on one hand and the hydrogen atom at the other? Because, of course, our understanding of it is very different, but in the end, we should get a very similar looking Schrödinger equation for the whole thing.
Well, at this level, I don't see any big difference. We just need our system to be scrambling, to be sufficiently complex. And that's it. But eventually, I would actually like to see some difference because the black hole is a particular type of a quantum system, different from the hydrogen atom. And I would like to see that difference in some quantities. I don't see it here in this setting.
But for instance, the kind of analysis that you performed here, can you do the same analysis for a hydrogen atom absorbing and emitting photons? For instance?
Yes, yes. It's a completely general story, but we have to make an assumption that at late times, the out-of-time order correlator follows a certain formula. And qualitatively, this assumption means that the system is non-integrable. The hydrogen atom might not be such a good example, but say helium atom or lead atom will be a better example.
Other questions?
Was there a lower bound on the complexity in terms of dA, not dr?
A lower bound in terms of dA. We don't have such a lower bound, but we expect the square root of dA and dr be the exact answer. But we don't have any rigorous results about that.
Thank you.
Yeah. I'm wondering about the last point you made here. As I understood the description you gave of the Grover-Fetch algorithm, it sounded like correlate of recurring projectors, which sort of get you from one subspace to the rotation.
Yeah.
If you think of it in that sense, could you map this problem to a frequency of a long-length correlator of projectors, which would then perhaps make more direct connection with the thing that stands for multiple shocks, which internal sources do the projectors for you.
Long-length correlation between projectors. Well, we can expand this W and WA, WD in terms of the projectors. The problem with the interpretation in terms of multiple shock waves is that this calculation does not correspond to classical geometries. It corresponds to superpositions of different classical geometries that are actually very different. That's why it's not obvious how to interpret it.
I think Alexei again.